Today we will talk about hypothesis tests for two means. This is part three of a three-part series for hypothesis tests. The main topic would be to talk about hypothesis test for paired data. So given two random samples, x1, x2, x3 up to xn and y1 up to yn, if we assume that the xi's are independent of the yj's, then under some additional assumptions, we could use the t-test to test the hypothesis for the difference of means. The relevant test statistic in this setting is given by capital T equals x bar minus y bar minus mu1 minus mu2 divided by the square root of s1 squared over m plus s2 squared over n. This statistic has the student's t distribution with nu degrees of freedom, and the formula for nu has been calculated earlier. This is an important test, and it has many applications, and an interpretation of this testing procedure can be as follows. Suppose we choose two random samples, x1, x2 up to xm, and y1, y2, y3 up to yn, coming from a fixed population independently. We can think of this as choosing two random samples of people from a population independently, and we'd like to test if a certain drug is actually effective. In this setting, we are going to give one of these groups, that is the group corresponding to XIs, the drug, that is treatment A, and we're going to give the other group, the one corresponding to the YIs, treatment B, which will possibly be a placebo. The two sample t-test in this context will try to answer the following question. Is there a statistically significant difference between treatment A and treatment B? Alternately, we would be interested in knowing if the difference that has been observed in taking the drug versus taking the placebo was in fact caused by taking the drug. Since all the samples were randomly selected from the population, it can so happen that the sample corresponding to X size consisted of healthy individuals, whereas the sample corresponding to Y eyes had a majority of unhealthy individuals. As a result, even though the YIs took the placebo and the XIs took the drug, the results of this test will not provide proper causal inference. Such a setting is not an isolated case. In fact, there are many experiments where we will fix a set of n experimental objects and then apply two treatments or observations to these experimental units, right? Maybe we might fix an individual, measure their weight before a certain weight loss regimen and after a weight loss regimen, and want to compare whether the weight loss regimen is effective. In this setting, we get pairs of data. We get the pair xi comma yi, where xi is a measurement before you took the treatment and yi is a measurement after you took the treatment. In this setting, we want to ask the question, is there a statistical difference between two treatments or observations applied to the same experimental unit or location? In the context of the example, is there a statistical difference in taking the weight loss regimen and causing actual weight loss? Since the XIs and YIs are usually applied to the same individual, they're not going to be independent of each other. And in this setting, the two sample t-test is not applicable, or if you apply it, the application is incorrect or the inference is useless. So what do? We have the paired t-test. The assumptions for the paired t-test are that the data consists of n independently selected pairs. These are pairs of the form xi, comma yi, that is x1, y1 through xn, yn. The expected value of all the xi's is going to be equal to mu1, and the expected value of all the yi's is going to be mu2. This is I ranging from 1 through n. And we will set di to be the difference within the pair xi comma yi. That is, di is going to be equal to xi minus yi for I ranging from 1 through n. In this setting, the di's will be also required to be normally distributed, having the normal distribution with mean mu d and variance sigma d squared. Here d is the difference x minus y. This is the difference within the pairs. Since the di's are assumed to be normally distributed, the expected value of all the di's is going to be equal to mu d, and it can be calculated to be mu1 minus mu2. This tells us that the expected value of the differences di is the same as the difference of the expected values of the random variables xi, yi. That is to say that the expected value of the random variable d is the same as the expected value of the random variable x bar minus y bar. Since the assumption about the pairs being independently chosen, we must have that the differences di also be independent of each other. A consequence of this is that the set d1, d2 up to dn of n random variables is going to be a random sample coming from a normal distribution with mean mu d and standard deviation sigma d. This would suggest that we use the one sample t-test. The paired t-test procedure is as follows. The parameter of interest is mu d, the mean difference between x and y. The null hypothesis is going to be that mu d equals delta naught, and the random variable over here of interest is x minus y, and mu d is going to be equal to mu1 minus mu2. The test statistic is d bar minus delta 0 divided by st over square root of n. This has the t distribution with n minus 1 degrees of freedom. And given sample data consisting of pairs small x1, y1, x2, y2 up to xn, yn, d bar is going to be the mean of the differences x1 minus y1, x2 minus y2, all the way up to xn minus yn. This is exactly x bar minus y bar. And st is the standard deviation of the differences x1 minus y1 up through xn minus yn. In this setting, the p-value can be calculated by working with the t distribution with n minus 1 degrees of freedom. There are three possible null hypotheses. The case when mu d is greater than delta 0 is going to correspond to a p-value calculated as the area under the t curve to the right of the test statistic t. In the case of the lower tail test, we are going to look at the area under the t curve to the left of the test statistic t. And in the case of the two-tailed test, the p-value is going to be twice the area under the t curve to the right of the absolute value of the test statistic t. In this setting, the test decision is going to be arrived at by comparing the p-value with the significance level. We will reject the null hypothesis if p is less than equal to alpha, and we will fail to reject the null hypothesis if p is greater than alpha. We finish up by comparing paired experiments with unpaired experiments. So suppose we have xi's where the expected value of xi equals mu1 and yi's where the expected value of yi equals mu2. The variance of xi is sigma 1 squared and the variance of yi is sigma 2 squared. We will let rho equal the correlation of x and y, and d is the difference x minus y. In this setting, note that the expected value of d is going to equal to mu1 minus mu2. This is the same as the expected value of x bar minus y bar. The variance of the random variable d can be calculated as the variance of x minus y. And now, since we're not assuming independence of x minus y, this equals to sigma 1 squared plus sigma 2 squared minus 2 times the correlation coefficient times sigma 1 times sigma 2. The variance of x bar minus y bar is going to be given by the following formula, and it's easy to note that this is going to be less than equal to the variance of x bar minus y bar if we were to assume that the xi's and the yi's were independent of each other and that the correlation coefficient rho was a positive number. A consequence of this calculation is that if there was positive dependence between the pairs, st divided by square root of n would be strictly less than the square root of s1 squared over m plus s2 squared over n, which is to say that the test statistic for the paired data would be bigger than the test statistic for the unpaired data, which corresponds to the two sample t-test. And this is a consequence because the numerator in both of these test statistics is the same. To summarize, we note that in this setting, we are more likely to have the p-test to reject the null hypothesis H0 stating that mu d equals delta 0 than to have the two sample t-test rejecting the null hypothesis that the difference of the means equals delta naught. Another way to say this is that the two sample t-test is more likely to undermine the significance of the data than the paired t-test. To summarize this video, we have introduced the idea and focused on the important scenarios where the paired t-test is applicable and its comparison with the inference coming from the unpaired t-test or the two sample t-test. We will talk more about these in a future video, but for now, this is all. Take care of yourselves, and I will see you around.